Here we're going to talk about electronegativity and polarity. Along with polarity, it can be quantified with something called the dipole moment. There's going to be partial charges, and then something that we call percent ionic character. So even if something isn't fully an ionic compound, it can have some amount of ionic character. So we'll talk more about that. So electronegativity described chemical bonds as ionic and covalent in the past. Ionic, as you know, occurs between a metal and a nonmetal, some cation and some anion. Covalent occurring between two nonmetals. These are actually just the extremes in a spectrum of bonding. So it's not that we lied to you, but there are some nuances here. It's not just ionic or covalent. It's not just black or white here. There actually is a spectrum. And many of these bonds, in fact, all bonds fall between these two extremes. And sometimes we can define them as ionic or covalent, but there's something in the middle that encompasses a lot of different bonds as well that we will call polar covalent bonds. So this would still be where the electrons are shared, which is what we defined as covalent, but not shared equally. So these electrons will be pulled closer to one atom or the other. Again, we call these polar covalent bonds. So now maybe we have three categories. We have ionic, polar covalent bonds, which almost have some ionic character to them. And then lastly, pure covalent, sometimes just called covalent. But there's kind of this intermediate category that we're now going to discuss and talk about. And there's ways that we can show that. So here's an example of a pure covalent bond, H2. These show electron density, where red is high electron density, blue is low electron density. So between H2, they're equally shared. The electron density lies between the two nuclei. So it's totally and utterly shared equally. There's no difference between one hydrogen and the other. So that's called a pure covalent. Looking all the way on the right-hand side, we have ionic bonding, which we're also familiar with. Sodium fluoride. Sodium is positively charged, fluoride is negatively charged. And you can see that there's all the electrons are, most of that electron density is around the fluorine, which makes sense. It's F- as opposed to Na+. So sodium is positively charged, fluoride's negatively charged, and that's why we see that discrepancy in color. Now there's some intermediate between these, however, right? So here's hydrogen fluoride, where there's actually still a partial negative charge on that fluorine and a partial positive charge on that hydrogen. There's an unequal sharing between that hydrogen and the fluorine. So it's not equal like H2, but it's not a total electron transfer like sodium fluoride. It's somewhere in between, and we call that a polar covalent bond. So instead of saying that there's a positive and a negative, like ionic bonding, we say that there's a delta positive, delta negative, which is called a partial positive or partial negative. So that's where you're seeing that lowercase delta Greek letter next to that positive charge. That means a partial positive and a partial negative. So again, we're defining that hydrogen as saying it's partially positively charged in this polar covalent compound. And the fluoride is partially negatively charged. Even though it's covalent, they are sharing these electrons. It is an unequal sharing, and that causes the discrepancy that we're seeing in those colors. So this pertains to electronegativity. Electronegativity is the ability of an atom in a compound to draw electrons to itself. So this is a little different than electron affinity, which it seems very similar, or ionization energy, and they are similar concepts, but this is the ability of an atom in a compound to draw electrons to itself. So these are bonding electrons. How easily can an atom draw bonding electrons towards oneself? So elements with high electronegativity have a greater tendency to attract electrons, these bonding electrons, than elements with low electronegativities. So because of that, if you have a high electronegativity, they are more likely to be partially negatively charged, than atoms with low electronegativity, which would tend to be partially positively charged in these polar covalent bonds. Like I said, it is related to electron affinity and ionization energy. So fluorine has a very, very high electronegativity. It is the highest electronegativity. And it also has a high electron affinity, and it tends to be able to accept electrons. So it's a similar characteristic, but not the same. Electronegativity is tending to pull bonding electrons towards itself. Electron affinity is actually accepting a new electron. Also, ionization energy, it's very hard to ionize fluorine. It does not want to lose electrons. So you can see how all these characteristics seem fairly similar, but they are distinct ideas. So we have to be a little bit careful with that. Just remember, with electronegativity, it's the ability to bring bonding electrons towards itself, which is different than electron affinity or ionization energy. So here is the general trend for electronegativity. So it increases up and to the right for electronegativity. And you can see there's some nominal values associated with electronegativity. The highest electronegativity is fluorine, and that's has a value of 4.0. And we're gonna, this is a chart that's on the back of your periodic table handout that you'll be able to use for quizzes and exams. You will need these numbers to do some fairly straightforward calculations. But we care about how big of a difference there is in electronegativity between two atoms to try and characterize that bond as being somewhere between ionic or pure covalent. And this is kind of a way to generally calculate that. This is another way to represent that electronegativity. You can see as we move from left to right, so lithium to fluorine, we have a big increase in electronegativity. We're increasing electronegativity as we go. But then down the periodic table, we do see a general downtrend. So fluorine being the highest, then you see chlorine is lower, bromine's lower, iodine's lower. So that would be going down the periodic table. So this is, you can see some of those. In terms of electronegativity, there's not an exact perfect, this is a totally made up line when we're distinguishing between nonpolar covalent and polar covalent, or between polar covalent and ionic. So we've developed some guidelines to help distinguish them. Again, they're just made up, but they are useful guidelines. So we have something that's nonpolar, which this would be a pure covalent bond. And that's when the electronegativities between the two atoms differ by less than 0.5. So we would call that purely covalent. Of course, if they're the same atom, they have the exact same electronegativities, so that will be certainly a nonpolar. But there are other examples of similar electronegative atoms that are characterized as nonpolar. So the difference between carbon and hydrogen is 0.4, and that is a classic example of a nonpolar bond. And it's a very common bond that we find, and that we characterize as purely covalent. Next, we have polar covalent. We say that this is when electronegativities differ in the range of 0.5 to 2.0. We call those polar covalent bonds if we're using this electronegativity definition. And then lastly, ionic, electronegativities that differ by 2.0 or more, generally considered ionic. And of course, this goes hand in hand with your prior understanding of what an ionic versus a covalent bond is. This is the best rule for finding a polar covalent bond, probably not as good of a technique for finding ionic bonds. There are plenty of what we would traditionally call ionic compounds that maybe technically show up in the polar covalent category. It still can be reasonably defined as an ionic bond if that's the case. So let's try a few of these. Let's classify these following bonds as nonpolar, which again just means pure covalent. Polar, again, means polar covalent, or ionic. So CLF, take a look at our chart. Fluorine is the highest at 4.0. Chlorine should be 3.0, so there's a change in electronegativity of 1.0. That is somewhere between 0.5 and 2, so that is a polar covalent bond. Fluorine is more electronegative, so we would even then represent fluorine as partially negative and chlorine as partially positive in that polar covalent category. Again, and that was with the delta negative, delta positive, which means partial negative, partial positive. All right, cesium bromide. We could probably guess cesium we know is a metal, bromide is non-metal, so it should be ionic. If you were to actually take a look at the change in electronegativity, cesium is 0.7, very, very low electronegativity, and bromine is relatively high at 2.8. So the difference is 2.1, so that is in the ionic category. So according to these definitions, it's still ionic. And the carbon-carbon double bond in C2H4, well, carbon and carbon both are the same thing. They both have the same electronegativity of 2.5, so that has no change in electronegativity, so that is a pure covalent bond. There is no discrepancy between the two, so there would be no partial positives or partial negatives. Those carbons are sharing those 4 electrons in that double bond perfectly, so those 2 carbons should be identical in that regard. So we can, we've already talked a little bit about partial charges here. There's another idea called dipole moment, and it can get us to something called percent ionic character. So the shift of electron density in a polar bond can be symbolized in 2 ways. We already showed the delta positive and delta negative. So hydrogen fluoride right there, or if it's aqueous, right, hydrofluoric acid, which is slightly different. This is hydrogen fluoride. So you have a partial positive on the hydrogen, which has a low electronegativity, and a partial negative on the fluorine, which has a very high electronegativity. So HF is considered polar covalent for that reason. Another way we can indicate that is with that dipole arrow. And you can see there's kind of a plus sign on one side of the arrow, and that's on the plus side of the bond. And then the arrow is always going to point towards the more electronegative atom. And it's going to be along those bonds. These are vectors. If you're familiar with vectors, they have a magnitude and a direction. So it's important that these arrows go in line with the bond that you're referring to. And a longer arrow would indicate a stronger discrepancy in the electronegativities. It would mean that there is a bigger discrepancy in charges. And we call that a dipole moment. Don't worry too much about a lot of these things, but we can actually quantify the dipole moment. It's a way to quantify that bond polarity. Again, that polarity is referring to how big of a positive, how big of a negative, partial positive is there on those individual atoms. And they're expressed in Debye units. I think that it's 1 to 8 is a pretty typical or 0 to 8 maybe for dipole moment in Debye's. Maybe 8's too high, but here are some molecules and their respective dipole moments if they were to be quantified. Generally, the partial positive and partial negative, or just some arrow with a relative size indicating how big of a discrepancy there is going to be just fine. So this brings us to percent ionic character. Essentially, just based on the quantified values, we can get some indication of the percent ionic character. Don't worry too much about this, but the general trend is that as you increase the electronegativity difference, you're increasing the percent ionic character. At some point, if something's perfectly ionic, it should have 100% ionic character. And if it's something has absolutely no electronegativity difference, it should have no percent ionic character. You can see there is a generally linear trend here, but there are some differences that will cause some issues. For example, ion size and polarizability of those ions can affect this. So that it's a little bit more complex than just determining the difference in electronegativities and all of that, but it is a good trend for helping us determine what's going on.